Welcome to the GATE 2027 Open Mock Test for Chemical Engineering, focusing on heat transfer. This test includes 15 carefully selected questions that are both conceptual and typical of what you can expect in the exam. To help you fully understand the material, complete solutions are included for every question. You can find this test and additional resources at engineersinstitute.com. Let's get started and sharpen your heat transfer skills. This mock test consists of 15 multiple-choice questions focused on heat transfer. Each question is equally weighted, and only one answer is correct for each. The questions are designed to be conceptual and reflect the typical difficulty level of the GATE Chemical Engineering exam, with options carefully chosen to challenge your true understanding. Make sure to attempt all questions before you check the answer key and detailed solutions at the end of this deck. We recommend you complete the test in about 30 minutes, which breaks down to roughly 2 minutes per question, mimicking the exam's pace. The solutions not only provide the correct answers, but also explain the governing equations and concepts, along with reasoning for why close options are incorrect. Good luck, and remember to give it your best effort before reviewing the solutions. Here we have a question about conduction and Fourier's law. Imagine a plane wall with thickness L, with its two faces kept at temperatures T1 and T2, where T1 is higher than T2. The thermal conductivity, K, is constant, and the system is in a steady state. The question asks what happens to the heat flux if we double the thickness of the wall while keeping everything else the same. According to Fourier's law for one-dimensional steady conduction, the heat flux is given by K times the temperature difference divided by the wall thickness, L. This means the heat flux is inversely proportional to the thickness. So, when we double the thickness, the heat flux is reduced to half its original value. Therefore, the correct answer is that the heat flux becomes half of the original value when the thickness is doubled. Let's talk about the concept of the critical radius of insulation for a cylindrical wire carrying current. When we add insulation to reduce heat loss, there's a specific critical radius, denoted as RC, which equals the material's thermal conductivity divided by the convective heat transfer coefficient. Now, if the outer radius of the insulation, R2, is less than this critical radius RC, something interesting happens. Adding more insulation in this case actually increases the total heat loss rather than decreasing it. This occurs because the increase in the wire's outer surface area allows more heat to escape through convection, and this effect outweighs the benefit from the added insulation thickness. Essentially, heat loss keeps increasing until the insulation reaches that critical radius. Once the insulation thickness passes this critical point, further adding insulation will then start to reduce heat loss effectively. So for any insulation thickness less than the critical radius, the total heat loss increases continuously towards a maximum. This is a key concept to remember when designing insulation for cylindrical objects like wires. Here, we're looking at the temperature distribution in a fin of infinite length, which loses heat by convection from its lateral surface. The key equation shows that the temperature ratio, theta over theta b, decreases exponentially with distance along the fin. The parameter m depends on the convective heat transfer coefficient h, among other variables. Now, the question is, if the convective heat transfer coefficient h increases while other properties remain constant, what happens to the fin's effectiveness? Fin effectiveness is given by the square root of Kp divided by Ha, where K is thermal conductivity, P is the perimeter, and A is the cross-sectional area. As h increases, the denominator becomes larger, causing the overall effectiveness to decrease. This means that in environments where convection is very strong, fins actually become less effective because the bare surface is already transferring heat quite efficiently. So, adding fins doesn't provide as much benefit, which is why the correct answer is that fin effectiveness decreases. Here we have a question about conduction and the Biot number. A spherical metal ball with diameter d is quenched in oil, and the Biot number, calculated as HD over 6K for a sphere, is given as 0.05. The question is asking which method is most appropriate for analyzing the cooling process. Now, the Biot number is a key parameter that compares the internal thermal resistance to the surface convection resistance. When Bi is less than 0.1, the internal thermal resistance is negligible, so the temperature inside the object can be assumed uniform throughout. Since our Biot number here is 0.05, which is less than 0.1, the lumped capacitance method, option B, is the best choice. This approach simplifies the analysis because it treats the sphere as if it has a single, uniform temperature, making calculations more straightforward. Other methods like finite difference or semi-infinite solid approaches are more complex and usually reserved for cases with higher Biot numbers where temperature gradients inside the object are significant. And Heisler charts, while useful in some scenarios, aren't mandatory or the only valid option here. So, in summary, because the Biot number is low, we can confidently apply the lumped capacitance method to analyze the cooling behavior of this spherical metal ball. Here we are focusing on the Prandtl number in the context of forced convection heat transfer. The Prandtl number, often seen in correlations like nu equals C times Re to the M times PR to the N, physically represents the ratio of momentum diffusivity to thermal diffusivity. This means it compares how quickly momentum spreads through a fluid versus how quickly heat spreads through that same fluid. To put it simply, it relates the relative thickness of the velocity boundary layer to the thermal boundary layer. Just to clarify, the Reynolds number represents the ratio of inertia force to viscous force. Grashof number compares buoyancy force to viscous force, and the Nusselt number represents the ratio of convective to conductive heat transfer. So here, the key takeaway is that the Prandtl number gives us insight into the balance between momentum and thermal diffusion in forced convection scenarios. Now let's talk about natural convection over a vertical heated plate and the significance of the Grashof number. The Grashof number essentially measures the balance between two key forces in this scenario. It represents the ratio of buoyancy forces, which are responsible for driving the natural convection flow, to viscous forces, which act to resist that flow. This ratio helps us understand how strongly the fluid will circulate due to temperature differences. In fact, the Grashof number in natural convection is analogous to the Reynolds number in forced convection, as both quantify the relative importance of different forces influencing fluid motion. So, in this context, option B, buoyancy force to viscous force, is the correct interpretation of the Grashof number. For laminar flow over a flat plate, when the Prandtl number is much greater than 1, like in oils which have high viscosity and low thermal diffusivity, the hydrodynamic boundary layer actually grows thicker than the thermal boundary layer. This means that the thickness of the velocity boundary layer, denoted as delta, is greater than the thermal boundary layer thickness, delta T. This relationship is captured by the approximate ratio delta over delta T being proportional to the Prandtl number raised to the 1/3 power. So, for high Prandtl numbers, delta is larger than delta T. Conversely, for very low Prandtl numbers like in liquid metals, the thermal boundary layer becomes thicker than the velocity boundary layer. Understanding this helps us predict heat transfer characteristics in different fluids. Here we have a question about radiation and black body loss, specifically the Stefan-Boltzmann law. We are given two black bodies at absolute temperatures T1 and T2, with T1 being twice T2. The question asks for the ratio of their emissive powers, E1 over E2. According to the Stefan-Boltzmann law, the emissive power is proportional to the fourth power of the absolute temperature, meaning E equals sigma times T to the fourth. So when we take the ratio E1 over E2, it becomes T1 over T2 to the fourth power. Since T1 is twice T2, this ratio is 2 to the power of 4, which equals 16. This illustrates how sensitive radiative emissive power is to temperature. It increases much faster than conduction or convection, which depend linearly on temperature difference. Therefore, the correct answer here is 16. Here, we're looking at the concept of view factors in radiation heat transfer, specifically for two infinite parallel plates facing each other. The question asks what fraction of radiation leaving surface 1 directly strikes surface 2, known as the view factor F12. Since the plates are infinite in size, all the radiation leaving surface 1 is intercepted by surface 2. None escapes into the surroundings. This means that the view factor F12 equals 1.0. It's important to note that view factors depend solely on the geometry of the surfaces involved, not on their emissivity or material properties. So, for infinite parallel plates, the answer is unequivocally 1.0. Here we have a question about the log mean temperature difference, or LMTD, in heat exchangers. For the same inlet and outlet temperatures of the hot and cold fluids. The key point is that the LMTD in a counterflow heat exchanger is always larger than or equal to that of a parallel flow exchanger. This happens because, in a counterflow setup, the temperature difference driving heat transfer is more evenly spread along the length of the exchanger. As a result, counterflow exchangers are more effective at transferring heat and can even cool the cold fluid to temperatures lower than the hot fluid's outlet, which parallel flow exchangers can't do. So, the correct answer here is that the LMTD is always larger or equal in counterflow compared to parallel flow. In the effectiveness NTU method, when we look at a heat exchanger with a capacity rate ratio, CR, equal to 1 in a counterflow arrangement, something interesting happens as the number of transfer units, or NTU, becomes very large. The effectiveness, which measures how well the heat exchanger performs compared to its maximum possible heat transfer, approaches a value of 1. This means the exchanger is nearly perfect in transferring heat, reaching its theoretical maximum efficiency. This is unique to the counterflow configuration with CR equal to 1, because the temperature profiles of the hot and cold streams remain parallel along the entire length of the exchanger, avoiding any temperature pinching and allowing maximum heat transfer. Here, we're looking at the pool boiling curve, which plots boiling heat flux against the excess temperature. The critical heat flux, or CHF, also known as the burnout point, is a crucial concept. It marks the exact moment where the heat transfer regime shifts from nucleate boiling to film boiling, passing through what's called the transition boiling region. Up to this point, bubbles form and detach efficiently, promoting effective heat transfer. However, once the CHF is reached, a vapor film completely blankets the heating surface. This film actually insulates the surface, causing the heat flux to drop sharply even as the temperature continues to rise. This drop is dangerous because it can lead to rapid temperature spikes on the surface, potentially causing damage. So, the key takeaway is understanding that CHF is the limit of efficient boiling heat transfer before this risky transition happens. According to Nusselt's theory of laminar film condensation on a vertical plate, the average heat transfer coefficient is inversely proportional to the plate height raised to the 1/4 power. So, when we double the height of the plate, keeping all other factors constant, the average heat transfer coefficient decreases to about 0.84 times its original value. This happens because as the condensate film thickens along the plate, it adds thermal resistance, which reduces the heat transfer rate per unit area. However, it's important to note that the total heat transfer actually increases since the surface area is larger, even though the heat transfer coefficient per unit area drops. Here we're looking at the Fourier number, which is used in transient or unsteady state conduction analysis with Heisler charts. The key point is that the Fourier number is a dimensionless time parameter. What it really tells us is how fast heat conduction is occurring compared to how much thermal energy is being stored in the material. If the Fourier number is large, it means heat has had enough time to travel deeply into the material, so the system is close to reaching steady state. On the other hand, a small Fourier number means we're still in the early stages of the transient process. It's important to note that the Fourier number is not about the ratio of internal thermal resistance to surface resistance. That's actually the Biot number. So, essentially, when you see the Fourier number, think about the time aspect of heat conduction relative to energy storage inside the body. Here we have two slabs of equal thickness but different thermal conductivities, K1 and K2, where K1 is greater than K2. When we arrange these two slabs in series to form a composite wall, the overall thermal resistance is simply the sum of the individual resistances. This means the higher resistance from the slab with lower thermal conductivity dominates, and all the heat flow has to pass through it. On the other hand, when these slabs are arranged in parallel, side by side, for the same overall heat transfer area, the overall thermal resistance is calculated differently. In this case, the resistances combine as the reciprocal of the sum of reciprocals, which results in a smaller equivalent resistance because the heat can preferentially flow through the slab with higher thermal conductivity. Therefore, for any two materials with different thermal conductivities, the overall thermal resistance is always higher in the series arrangement than in the parallel arrangement. This principle is similar to how resistance works in electrical circuits, where resistors in series add up and resistors in parallel reduce the total resistance. So, the correct answer here is that the thermal resistance is higher for the series arrangement than for the parallel arrangement. Here is a quick overview of the answer key for the questions. For questions 1 through 4, the correct answer is option B, and all relate to conduction. This shows how important understanding conduction is in this section. Moving on to questions 5 through 7, the answers shift to B and C, focusing on convection. This highlights how convection concepts are also essential. Questions 8 and 9 have answers of D and C, respectively, and focus on radiation, emphasizing the significance of heat transfer through radiation. Question 10's answer is B and covers heat exchangers, as does question 11 with answer D. Question 12 is B and relates to boiling heat transfer, while question 13's answer C deals with condensation. Finally, questions 14 and 15 return to conduction with option B as the correct answer. This summary helps you see which topics are emphasized across the questions and where to concentrate your study efforts. Here we have a classic conduction problem based on Fourier's law. We're looking at a plane wall with thickness L and its two faces held at temperatures T1 and T2, where T1 is higher than T2. The key point is that everything else remains constant: the temperatures and the thermal conductivity K. Now, when the thickness of the wall is doubled, what happens to the heat flux? According to Fourier's law, the heat flux is proportional to the temperature difference divided by the thickness. Mathematically, it's Q double prime equals K times T1 minus T2 divided by L. So, if the thickness L doubles, the heat flux doesn't stay the same. It actually gets cut in half. This inverse relationship means that heat finds it harder to pass through a thicker wall, reducing the flux by 50%. That's why the correct answer here is option B. The heat flux becomes half of its original value. This principle is fundamental when designing insulation or any system involving heat transfer through solids. Here, we're looking at the concept of the critical radius of insulation for a cylindrical wire carrying current. When we add insulation to such a wire to reduce heat loss, there's a critical radius, denoted as RC, which is calculated as the thermal conductivity K divided by the convective heat transfer coefficient H. Now, if the insulation thickness is increased but the outer radius, R2, remains less than this critical radius RC, the total heat loss from the wire actually increases. This happens because the outer surface area grows more quickly than the increase in conduction resistance, leading to more heat being lost. This continues up until R2 reaches RC, which represents the maximum heat loss point. Beyond this critical radius, adding more insulation then starts to effectively reduce heat loss. So, the key takeaway is that for insulation thicknesses where R2 is less than RC, increasing insulation will always raise total heat loss before eventually reducing it once we pass that critical radius. Here, we're looking at the behavior of a fin of infinite length losing heat through convection along its surface. The temperature distribution along the fin is described by this exponential relationship, where theta over theta sub b equals e to the negative mx. The key factor m depends on the convective heat transfer coefficient h, the fin's perimeter P, thermal conductivity K, and cross-sectional area A. Now, if we increase the convective heat transfer coefficient H while keeping K, P, and a constant, what happens to the fin's effectiveness? The fin effectiveness, denoted by epsilon, is proportional to the square root of K times P divided by H times A. This means as H increases, the denominator gets larger, causing the overall fin effectiveness to decrease. In practical terms, when the convective heat transfer coefficient is high, the surrounding environment already removes heat efficiently from the surface without needing the extended area provided by the fin. Therefore, the fin becomes less effective under these conditions. So, the correct answer is that the fin effectiveness decreases as H increases. Here we have a spherical metal ball with diameter d being quenched in oil, and the key parameter we're looking at is the Biot number, defined here as by equals H times D divided by 6K. In this case, the Biot number is 0.05. Now, the question is which analytical approach is most suitable for studying the cooling process. The correct choice is the lumped capacitance method, also known as the lumped parameter method. This approach works best when the Biot number is less than 0.1. That threshold indicates that the internal resistance to heat conduction within the sphere is much smaller than the resistance to heat transfer at its surface by convection. Since our Biot number is 0.05, which is well below 0.1, we can safely assume that temperature throughout the sphere remains uniform throughout the cooling. This simplification means we don't have to consider spatial temperature variations inside the sphere, making our analysis much more straightforward and accurate using the lumped capacitance method. Let's talk about the Prandtl number in the context of forced convection heat transfer. In correlations like nu equals C times Re to the M times PR to the N, the Prandtl number actually tells us about the ratio of momentum diffusivity to thermal diffusivity. To break that down a bit, PR is defined as the kinematic viscosity divided by the thermal diffusivity, or more specifically, as mu times Cp divided by K. What this means physically is that the Prandtl number compares how thick the velocity boundary layer is relative to the thermal boundary layer. It's important to keep in mind how this fits with the other dimensionless numbers we use. The Reynolds number relates inertial forces to viscous forces, while the Grashof number deals with buoyancy versus viscous forces. Meanwhile, the Nusselt number tells us about the ratio of convective to conductive heat transfer. So, understanding the Prandtl number helps us see how momentum and heat are transported differently in fluid flow. Here, we're discussing the concept of natural convection, specifically over a vertical heated plate. The key point is the Grashof number, which essentially quantifies the relationship between two important forces at play. It represents the ratio of buoyancy forces, which cause the fluid to move due to density differences from temperature variations, to the viscous forces, which oppose this motion. So, a higher Grashof number means buoyancy is more dominant, leading to stronger natural convection currents. This is similar to how the Reynolds number functions in forced convection, but here it's all about the balance between buoyancy and viscosity. Understanding this helps us predict how fluids will behave when heated naturally, without any external force driving the flow. Let's look at the relationship between the hydrodynamic and thermal boundary layers in laminar flow over a flat plate, when the Prandtl number is much greater than 1, like in oils. The key point here is that the hydrodynamic boundary layer thickness, which we denote as delta, grows larger than the thermal boundary layer thickness, delta T. This happens because the ratio of delta to delta T is approximately the Prandtl number raised to the 1/3 power. When the Prandtl number is very high, meaning the fluid has high viscosity and low thermal diffusivity, the velocity boundary layer expands much faster than the temperature boundary layer. So, in this case, delta is greater than delta T. Conversely, for very low Prandtl numbers, such as with liquid metals, the thermal boundary layer is thicker than the hydrodynamic one. The correct choice here is option C, confirming that delta is greater than delta T under these conditions. Here, we're looking at two black bodies at different absolute temperatures, T1 and T2, with T1 being twice T2. The question is about the ratio of their emissive powers according to the Stefan-Boltzmann law. This law tells us that the emissive power, or the energy radiated per unit area, is proportional to the fourth power of the absolute temperature. So, when we calculate the ratio E1 over E2, it becomes the ratio of their temperatures raised to the fourth power. Since T1 is twice T2, we have 2 to the fourth power, which equals 16. This clearly shows that radiation depends very strongly on temperature, much more than conduction or convection, which change linearly with temperature difference. The key takeaway is that even a small increase in absolute temperature results in a significantly larger increase in radiative energy emitted. Here we are looking at the concept of the view factor in radiation heat transfer, specifically for two infinite parallel plates facing each other. The view factor, denoted as F12, represents the fraction of radiation leaving surface 1 that directly hits surface 2. For infinite parallel plates, the key point is that all the radiation emitted from surface 1 is intercepted by surface 2 because the plates extend infinitely and there are no gaps or edges where radiation can escape. This means the view factor F12 is equal to 1.0. It's important to understand that view factors are purely geometric. They depend solely on the shapes and orientations of surfaces relative to each other, and not on properties like surface emissivity. Therefore, the correct answer for this problem is option C, which states the view factor is 1.0. Here we're looking at the difference in log mean temperature difference, or LMTD, between counterflow and parallel flow heat exchangers when the inlet and outlet temperatures of both fluids are the same. The key takeaway is that for these conditions, the LMTD in a counterflow heat exchanger is always larger than or equal to that in a parallel flow exchanger. The reason is that in counterflow, the temperature difference between the hot and cold fluids remains more consistent along the length of the exchanger. This more uniform temperature driving force allows for more effective heat transfer. In fact, a counterflow exchanger can even cool the cold fluid to a temperature below the hot fluid's outlet, something that simply can't happen in parallel flow. So, when you want maximum heat exchange efficiency, counterflow is the preferred choice. Let's focus on the effectiveness NTU method for heat exchangers, specifically for a counterflow configuration where the capacity rate ratio, CR, equals 1. Here, CR is defined as the minimum heat capacity rate divided by the maximum, and when CR equals 1, both fluid streams have equal capacity rates. The formula for the effectiveness, epsilon, in this case is NTU divided by 1 plus NTU. As the number of transfer units, or NTU, becomes very large, approaching infinity, the effectiveness approaches 1.0. This means the heat exchanger reaches its maximum theoretical heat transfer efficiency. This is unique to the counterflow setup because the temperature profiles of the fluids remain parallel along the entire length of the exchanger, avoiding any temperature pinch points and allowing for complete heat transfer efficiency. So, the correct answer here is option D, confirming that the effectiveness approaches 1.0 under these conditions. Here we're looking at the concept of boiling heat transfer, specifically focusing on the pool boiling curve, which plots boiling heat flux against the excess temperature. The key point here is the critical heat flux, often called the burnout point. This is a crucial transition where the boiling mechanism shifts from nucleate boiling to film boiling, passing through what's known as the transition boiling region. At this burnout point, the heat flux reaches its peak, but beyond it, a vapor film forms continuously over the heating surface. This vapor layer acts as an insulator, causing the heat flux to drop sharply even though the surface temperature keeps rising. This situation is especially dangerous in practical applications because the surface temperature can increase rapidly, risking damage to the equipment. So understanding this transition and the critical heat flux is essential for managing safe and efficient boiling heat transfer processes. Here, we're looking at film-wise condensation on a vertical plate based on Nusselt's theory. The key point is how the average heat transfer coefficient, H_average, changes when we double the plate height. According to Nusselt's theory for laminar film condensation, the average heat transfer coefficient is proportional to the plate height raised to the power of -1/4. So, when we double the plate height, H_average decreases to about 0.84 times its original value. This happens because as the condensate film grows thicker along the plate, it creates additional resistance to heat transfer. However, even though the average coefficient decreases, the total heat transfer still increases since the surface area of the plate, where condensation occurs, is larger. This subtle balance between film thickness and plate size is essential to understanding heat transfer in condensation processes. Here, we're discussing transient or unsteady state conduction using Heisler charts, with a focus on the Fourier number. The Fourier number, defined as alpha times time over characteristic length squared, is a dimensionless parameter that represents the ratio of heat conduction to heat storage within the body. In simpler terms, it tells us how quickly heat is spreading through the material compared to how much heat is being stored. When the Fourier number is large, it means the conduction has progressed significantly, and the temperature is approaching steady state. Conversely, a small Fourier number indicates the conduction process is still in its early stages. It's important to note that while the Fourier number measures this time-dependent conduction behavior, the Biot number, which is different, relates to the resistance between the surface and the interior of the object. This distinction is key in analyzing transient heat conduction problems accurately. Here we're looking at the thermal resistance of composite walls made from two slabs with different thermal conductivities. When these slabs are arranged in series, meaning one after the other, the total thermal resistance is simply the sum of the individual resistances. This is because heat has to pass through both slabs sequentially. So the lower conductivity slab, which has higher resistance, dominates and affects the entire heat flow. On the other hand, when the slabs are arranged in parallel, side by side, the heat can flow preferentially through the slab with higher conductivity, lowering the overall resistance. In this case, the total resistance is found by combining the resistances inversely, similar to parallel electrical circuits. The result is always a smaller thermal resistance compared to the series arrangement. Therefore, for any two slabs with different conductivities, the overall thermal resistance in series will always be higher than in parallel. This is a fundamental property of resistance networks and helps us understand how arranging materials affects heat transfer efficiency. If you're preparing for GATE 2027 in chemical engineering, the GATE online mock test from Engineers Institute of India is an excellent resource. It covers all essential subjects like chemical reaction engineering, heat transfer, mass transfer, process calculation, and thermodynamics, among others. The program offers over 4,250 questions with various formats, including MCQs, MSQs, and NATs, spread across 75 subject-wise and full-length tests. What makes this series stand out is the detailed solutions and in-depth performance analysis that helps you understand your strengths and areas for improvement. The tests are designed according to the latest GATE pattern and difficulty level, ensuring you get a realistic experience. Plus, you'll use a real GATE interface complete with a virtual scientific calculator to simulate exam conditions. You can also track your progress throughout your preparation and predict your All India rank, which is a great way to stay motivated and focused. To enroll, simply visit the Engineers Institute website or scan the QR code provided. This dedicated coaching and structured approach can make a significant difference in your GATE preparation journey. If you're aiming to crack the GATE chemical engineering exam, our program offers expert mentorship from experienced faculty with over 15 years in the field. At Engineers Institute of India, we provide dedicated coaching specifically tailored for GATE 2027 chemical engineering. Our comprehensive course includes online live classes, recorded video lectures, and well-structured study materials to support your preparation. You can even attend a free live class to get a feel for our teaching style. To enroll or learn more, visit our course page at www.engineerinstitute.com or contact us at 999-035-7855. We're here to guide you every step of the way towards your GATE success.